What's up everyone, welcome back. Patrick here, moving on to the next example dealing with linear optimization. This one is going to be a hectic one. This is going to be a word problem, so probably going to be a fairly long video if I'm guessing. And I'm going to try to go through as much detail as I can and explain my process when I get a question like this. If you're fairly comfortable with these kinds of questions, you may want to skip ahead to the most important parts where we get the feasible region and then when we do the actual maximization, etc. But for those of you that are kind of still new to these kind of word problems, I'm going to go through in detail my process. So it may take quite a while, but hopefully by the end of it, you get a better understanding of how to go about these questions when you get them. So let's read what's going on. We got a company that produces two products, A and B. 3 machines are used to create both products. Each unit of A requires 3 hours of machine 1, 2 hours of machine 2, and 1 hour of machine 3. Each unit of B requires 2 hours of machine 1, 3 hours of machine 2, and 5 hours of machine 3. The total capacity for machines 1, 2, and 3 are 240 hours, 210 hours, and 280 hours respectively. Each unit of products A and B earns $6 and $10 in profit respectively. How many units of each product should be produced to maximize the profit? All right, so lots going on. Now, the first thing that I always start with is creating my variables. And I mean, there's lots of stuff going on here. So sometimes it might be confusing to think of what am I going to set my variables as? Is it going to be machine hours? Is it going to be products or what? And usually you could get it with whatever they're actually asking in the question. And notice that that's the last sentence. So notice they're asking how many units of each product, and there's 2 products, right? A and B, should be produced to maximize the profit. And so that tells you right there what the variables are going to be. So I'm going to let X be the number of units of product A, and then I'm going to let Y be the number of units of product B, like that. So there's actually only 2 variables because there's only 2 products, right? So even that step alone sometimes can be confusing for people, right? And so usually you want to read the last sentence to know what they're asking for, and usually what they're asking for, that's what you're going to set your variables as. So now that we have our variables set, let's go into detail of what they're talking about or what they're saying about products A and B. So we're told that 3 machines are going to be used to create both products. And then specifically for product A, they're saying that it requires 3 hours of machine 1, 2 hours of machine 2, and 1 hour of machine 3. So what I'm going to do here is I'm actually going to set up a table to show this a little bit better in a more visual sense. So let's say we'll represent the columns as products A and B. And there are 3 machines used, right? So, okay, this is going to be row 1, is going to be machine 1. This is going to be machine 2. And then this is going to be machine 3. Just so we could organize our thinking a little better versus trying to always refer to the paragraph. So, okay, each unit of A requires 3 hours of machine 1. So, each unit of A requires 3 hours of machine 1, 2 hours of machine 2, and 1 hour of machine 3, like that. Each unit of B requires 2 hours of machine 1, 3 hours of machine 2, and 5 hours of machine 3. Okay, next piece of information, we're told the total capacity for machines 1, 2, and 3 is 240 hours, 210, and 280 hours respectively. So the machines are represented with these rows, so why don't we put another column here for total capacity. And we're told the total capacity for machine 1 is 240 hours, so that's going to be here. The total capacity for machine 2 is 210 hours, and then for machine 3, it is 280 hours, like that, right? Machine 3, 280, 210, etc. And then lastly, they say each unit of products A and B earns $6 and $10 in profit respectively. So let's put another row here for profit. A earns $6 in profit. Each unit of product A earns $6 in profit here, and $10 for product B, like that. Okay, and so now we have a nice table here representing this paragraph, and I feel like this is a lot nicer and easier to look at than to continue to go through the paragraph and get the information that we need. And so from this point, we just have to refer to this table, and now we can go into creating basically our maximizing function. Remember, we're maximizing the profit, and then creating our constraints. So we're maximizing the profit, right? So what we're going to be trying to do is we're going to try to maximize 6x plus 10y, like that. Because remember, the number of units for A we represented as x, and the number of units of B we represented as y. So each unit of product A makes $6 in profit. So the total profit coming from product A is going to be $6 per unit times the number of units of A. And then same thing for B. Each unit makes $10 in profit. So the total profit coming from product B would be the $10 per unit times the number of units of B. And so we're trying to maximize that total profit right there. So that comes from this row right here. So that's our maximizing function. And now over here on the side, we're going to have some constraints, right? Because we're told that each of these machines, machine 1, 2, and 3, they have a capacity. And so what that means is that we can't go over these hours for these 3 machines, right? Machine 1 has a capacity, a total capacity of 240 hours. So we can't exceed that. So the number of hours that's going to be used by machine 1 has to be less than or equal to 240, right? So each unit of A requires 3 hours of machine 1. So the total hours that that product A would consume would be 3x, right? 3 hours per unit times the number of units plus the number of hours product B would consume for machine 1 would be 2y. And this here has to be less than or equal to the total capacity for machine 1, which is the 240, like that. Okay, and then following that same process, 2x plus 3y is less than or equal to 210, and then x plus 5y is less than or equal to 280, like that. And then also x and y have to be greater than or equal to 0, right? You can't be producing a negative unit, right? So x has to be greater than or equal to 0, y has to be greater than or equal to 0, our variables. And so these are our constraints right here. So we're trying to maximize this right here with these constraints. And notice that now, at this point, we basically don't even have to refer to the word problem anymore, because now this just becomes an abstract linear optimization problem where we're just dealing with equations. We don't even have to refer to the problem. Maybe at the end when you make a concluding statement, right, you would say, okay, the number of units produced for A is this, number of units produced for B is that. But in terms of from now until the end of the question, you don't have to worry about the word problem. You just have to treat this like an abstract linear optimization problem with variables and equations. So the next step here, what I'm going to do is I'm going to take these constraints here and we're going to graph basically our feasible region. So first thing you want to do is you want to take each of these lines. So I'm going to take the first one, which is 3x plus 2y, And then we want to forget about the sign here. When we graph the feasible region, we'll bring this inequality sign back. You just want to put an equals. You want to treat it just like a regular line right here. 3x plus 2y is equal to 240. And what I like to do personally is I like to calculate the x and the y intercepts. So for the x-intercept, we're going to plug in 0 for the y, solve for x. And for the y-intercept, we're going to plug in 0 for x, and then solve for y. So if I plug in 0 for y, 2 times 0, this is going to go to 0. 3x equals 240. Divide both sides by 3, we would get an x-intercept of 80. And then for the y-intercept, plugging in 0 for x, 2y equals 240. Divide both sides by 2, we would get a y-intercept of 120, like that. So that's going to be the first line. Let's maybe do these in different colors. So next one, we'll have 2x plus 3y is equal to 210. So if we get the x-intercept, plugging in 0 for y, 2x equals 210, that would give us an x-intercept of what, 105? Like that. And then if we want to get the y-intercept, plug in 0 for x, 3y equals 210, y-intercept would be 70. Like that. And then this last line, we will have x plus 5y is equal to 280. Okay, so if we plug in 0 for y to get the x-intercept, we'll just get x equals 280. Like that. And if we plug in 0 for x and solve for y, so 280 divided by 4 would give us what? 56. So that would be the y-intercept right there. And so at this point, what I am going to do is I'm going to take these 3 lines here and I am going to graph this. And if you can, I know here that I have software and it's a little bit easier for me, but if you could have like 3 different colors of different pens when you're doing this, it can help you see more easily which points of intersection we're going to have to end up solving for, and you'll see further once we make these actual lines. That's the first thing I want to mention. Now, second thing is when you're making these, you want to try to make your axes to scale as much as possible. Okay, so try to have like even spaces, make them go up by the same amount, and then have even spaces as much as you can. If you have graph paper, that's great, but if you don't, try to make it as to scale as possible, and I'm going to explain why. Basically, let me explain now. It's because sometimes once you see your feasible region, there's going to be points of intersection that you're not going to have to solve for, that you don't have to waste time solving. And you could really see those if your graph is to scale. Sometimes if your graph is not to scale, you'll see points of intersection and you may think that it's in the feasible region when really it's not. Okay, but if you make them to scale, you'll see clearly which points are in the feasible region and which points aren't. So let me graph this and you'll see in a sec. So let's graph this first line, this blue one. So we have a y-intercept of 120, so that's going to start up here. And then we're going to have an x-intercept of 80, which is going to be about right here. Again, it doesn't have to be exact if you don't have graph paper, but it does help to make it as much to scale as possible. So now the red line, okay, 0 and 70, that's right here in the middle. And then 105 and 0, let's say that's like right here. Okay, so that's this line. Okay, why does this keep doing that? Okay, let's take that out. And then the last line, the x plus 5y, that had an x-intercept of 280, which is all the way over here, and a y-intercept of 56. Now 56, that's going to be like right here, let's say, and then all the way to 280, that's going to be like right there. Okay, so that there is our graph of the constraints. Now, where is our feasible region going to be? So this is where those inequality symbols are important. Now remember that the inequality symbols we had was less than, right? Because the 240, the 210, and the 280, those were all capacities, maximum capacity, so our hours had to be less than that. So that means that we cannot exceed these lines to the right, any of these lines, the red line, the green line, or the blue line, right? And so if you think about it, our feasible region is going to be right here. Okay, and so what's going to be the points of that feasible region? I'm going to erase that in a sec just so you can see the points clearly. Well, it's going to be this point, this point, this point here, this point here, and then the origin you always include as well, right? Those are the vertices of this feasible region. Now, why can't we go like here, for example? Well, over here, notice that we're less than this line, the green line, which is fine, but we're exceeding the blue line and we're exceeding the red line. So that's not going to work, right? It's going to fail these constraints over here. Okay, what about, why can't we go here? Well, it's below the green line, it's below the blue line to the left of them, but it's above the red line. So it's going to fail this constraint here, right? It has to be to the left of all of the lines, right? This one here is not going to work because we are above the red, to the right of the red, and then to the right of the green. Okay, we're to the left of the blue, it satisfies that constraint, but it's failing these two constraints. Over here, we're satisfying the blue constraint, satisfying the red constraint, but we're failing the green constraint, right? Because it's to the right of the green. So it has to be to the left of all the lines, and so the only region that satisfies that is basically this region right here, and the vertices of that region are these points that I highlighted in white here. Okay, now the thing that I want to mention, why I was really pressing before, why you wanted to have it to scale as much as possible, is because notice that this point over here, we don't have to waste our time finding that point of intersection between the blue line and the green line because it's outside of the feasible region. And if you don't make your graphs to scale, okay, so like let's say maybe we put this green line like a little further over here, right? The 280 was about there, but if we put it further down here, maybe this green line would have intersected like over here, for example, and you may think that, okay, I have to find that point of intersection, okay? But if you make it to as scale as possible and kind of make a big graph, as big as you can on your paper, you can clearly see which points you need to find and which points you don't have to waste your time with, right? And so you're not going to waste time finding this point here, this point of intersection between the blue line and the green line. So now let's go into finding all of these vertices of the feasible region. Well, this one is super easy. That's 0 and 0. This one here is easy as well because it's the y-intercept of the green line. So that's 0 and 56. And then this one is easy because it's the x-intercept of the blue line, which is 80 and 0. So we're going to have to test those points. Now what we have to do is we have to find what this point of intersection is and what this point of intersection is. So starting with this one, the red line and the green line, right? So let's write out those equations. We got 2x plus 3y is equal to 210. That's the red line. And then the green line is x plus 5y is equal to 280, like that. So substitution or elimination, I'm going to isolate for this x value. So I'll have 280 minus 5y, plug that in here. So just be careful with your algebra. Plus 3y is equal to 210. This would be what, 560 minus 10y plus 3y is equal to 210. Like that, right? Yeah. Okay, this is going to be negative 7y. Bring that over, positive 7y. 360 minus 210, when we bring the 210 over, that's going to give us what, 350. And so notice that y is going to be 50. And then if I plug in this y here, I'll get an x value of 30. So this point here is 30 and 50. That's the point of intersection between the red line and the green line. So that's going to be a point we're going to have to test 30 and 50. And notice that, again, another benefit of trying to make your graph to scale is you can see, does this point make sense? Right? It's not fully to scale, but yeah, 50, 30, I can be pretty confident that that is the correct answer. And if you want to be fully confident, you could take that x and y, plug it into both lines, make sure left side is equal to right side, right? You could plug it into these initial equations to make sure that that is the correct point. So the next point of intersection we have to find is this one over here between the red line and the blue line. And so I took these two, I put them here. So whichever way you want to do this, I think what I'm going to do is over here, I'm going to divide everything by 2 to get the y by itself. So we'll have 1.5x plus y is equal to 120. So that means y is going to be 120 minus 1.5x. And then I'm going to plug that in for this y here, right? So we'll have 2x plus 3, 120 minus 1.5x is equal to 210, like that. So we'll have 2x plus 360 minus 4.5x is equal to 210, like that. Okay, 2x minus 4.5x is a negative 2.5x, so bring that over, so that'd be positive. 2.5x, bring this over. 360 minus 110 would give us 150, like that. And then if we divide both sides by 2.5, 150 divided by 2.5 is what? 60, right? Okay, so x is 60, plug it in here to get the y value. 120 minus 1.5 times 60, 120 minus 90, which would give us 30. So the y value would be 30. So this point here would be 60 and 30, like that. And so that's going to be one of the other vertices that we have to test. And so from here, all we have to do is see what profit, this is our profit function, are we going to get from these vertices of the feasible region, and which one's going to give us the maximum profit, right? So we can maybe put like P is equal to 6x plus 10y. And so what would the P value be if we plug in 0 for x, 0 for y? Well, for this vertice, it's obviously going to be 0. Okay, for this one, plugging in 0 for x, 56 for y, that profit would be 560, right? So if we produce no units of product A and 56 units of product B, that's going to be our profit. And then over here, the other intercept, if we produce 0 units of product B, plugging in 0 for y, plug in 80 for x, our profit there would be 6 times 80, which is 480, like that. And then over here, the points of intersection that we found, plugging in 30 and 50, we'll have what? 180 plus 500, which gives us 680. And then over here, plugging in 60, so 360 plus 300, right? 30 times 10 plus 60 times 6, that would give us 660, like that. All right, so these were fairly close, but notice that the maximum profit is happening here. So it's happening at this vertice. So our maximum profit is $680, and it's going to happen if we produce 30 units of product A, because that's the x value, that's what we let the x value be, and 50 units of B, like that. And that is also going to ensure that we don't exceed our capacity for the 3 machines, right? So it's within the constraint, and that's the maximum profit that we're gonna get. And that's a wrap for the video. Hopefully you enjoyed that. If you want to see more videos like this, please go to my website, allthingsmathematics.com. Over there, all of the videos are organized by chapter, by section. If you feel like you need tutoring at any point, you could also hit me up. My contact details are on the website. Enjoy your day, and I'll see you in the next one. Peace out.